Good afternoon, class. We are continuing with Module 3, practice test number 3, which covers chapter 6 and 7. We are looking at chapter 6, normal probability distribution. This is the second part of that. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? And again, word problem, let's write the given symbolically. We are dealing with ND, short for normal distribution. Mu is 100, sigma is 15. So probability of X larger than whatever this number is, which is 120. And so now we are going to go with the Z score of X minus mu over sigma. See, when you write the information here, it makes life easier to follow. X is 120, mu and sigma are here. Plug in gives us 1.33. So we want the probability of Z to be larger than 1.33. It's a good practice to do the graph. So you locate the 1.33 somewhere between 1 and 2, and you shape the region. Now, clearly, this area is less than 0.5. The idea is that if you're reading a table or if you're doing the technology and it gives you a number which is off, you should recognize that. So with that being the case, you get 0.918 from the table. And since they ask for the percentage, we are going to change it to 9.18%. What is the maximum IQ score for the bottom 30%? We start with the graph. Again, it doesn't have to be perfect, but the idea is that this area if there is 30% or 0.3. So the idea is that to find the Z from the table or the technology, and then in this formula class, we want to find X. So we find the Z from the graph. In this formula, we want to find X. We already have mu and sigma, so the cross product will do the job. So from the table, we have somewhere between these two numbers. And here's the Z score, which means if I do the cross product, I get X minus mu is Z sigma. If I move the minus mu to the right, becomes this formula. So you should know this formula from here. So replace the mu with 100, replace the sigma with 15, and find a number in between, for example, minus 0.525, and it gives you this score. Obviously, because it's less than 0.5, this number should correspond to a score less than mu, and it does. Now, if we were to use the technology, so the maximum IQ score for the bottom 30% is this number, 92.125. And if they ask you to do the rounding, you do it accordingly. If we were to do the technology, area is 0.3, mu is 100, sigma is 15. You can go directly to the proper, to the given mu and sigma, and it will give you the answer. But it is important to do the graph, write the formulas, and then use the technology, because you're telling your reader you know exactly what you're supposed to do. Could somebody read this question, please?
Men have head breadths that are normally distributed with a mean of 6 in and a standard deviation of 1 in.
Inch.
1 inch, sorry.
Sure.
If a man is randomly selected, find the probability that his head breadth is less than 6.2 inches.
Perfect. So first and foremost, what is given. When you read the question, take enough time to write the given. This is a normal distribution. Mu is 6.0, sigma is 1.0. Write the given. Then what do we want? Probability of X less than 6.2. Well, we're going to go with the z-score, which is X minus mu over sigma, where X is going to be 6.2, mu and sigma are given. And so the normal distribution changes to a standard normal distribution, SND, with z being 0.2, so probability of z less than 0.2. It is highly recommended you do the graph. So this is the general case. Roughly, this is 0.2. It doesn't have to be to scale. So you're looking for this area, which is going to be a little bit more than 0.5 and 0.5793 from the table. I look at the same question. The change we are going to make is that in this case, we had a man. Now we have 100 men. So if 100 men are randomly selected, find the probability that their head breadth mean is less than 6.2. So it's the same question. We are changing one subject to so many. It doesn't matter how many. The fact of the matter is it's the same thing, but n is 100. So that's the main thing I want you to pay attention to, because n is 100. Instead of x, we're going to use x bar. So n is 100. And the formula is equals x bar minus mu of x bar over sigma of x bar, where mu of x bar is the mean of the samples, and sigma of x bar is the standard deviation of the samples. And mu of x bar is always equal to mu. Sigma of x bar is sigma over square root of n. I will go over that again in the following questions. So x bar is 6.2. Mu of x bar is the same as mu, which is 6. But sigma of x bar is sigma over square root of n. So let me write this. Mu of x bar is mu. Sigma of x bar is sigma over square root of n. All right. When we do the math, you may recognize that this is a complex fraction. And so as a result, the square root of 100, which is 10, gets multiplied by that, and it gives you 2. This is simple math. I hope everybody's okay with complex fractions, not a big deal. So again, this is 10, so it gets multiplied by the numerator. And so now the probability of z less than 2, so we go all the way to 2 now, which is a much larger area. And so 0.977. The difference between the two, and you want to be very careful with that. In this case, we are dealing with one subject. In this case, we are dealing with more than one. When it's more than one, we write the n, and instead of here using probability of x, use probability of x bar. Again, one subject versus more than one subject. If we were to use the technology. So for the lower, if you don't put anything, they use this number, and this means exponential 10 to the power of 99. This is negative, okay? And so, but as I said, you can use minus 100 or minus 1000. The upper is 6.2, mu is 6, sigma is 1, and if you paste it, it gives you the same answer as here. Take a look at this answer. Take a look at what we have. So if you look at number 2, next to it is 5, goes up to 3. So this is by table. This is, of course, much better by the technology, but you have to sure work within reason. If we want to go for the second part, now The difference between these two, I hope you see that the difference is that the sigma, now it's sigma of x bar, which is 1/10 in essence, 1/100 to the power of 0.5. And I left it in the same format just to make a point. You could get to the answer using normal CDF. And again, if you look at the fourth one, it's number 2 next to it is 4, so it doesn't change. So you have the same answer. Of course, this is table, this is technology, and it's a better approximation. Could somebody read this, please? Go ahead, class. Somebody read this, please.
The assets in billions of dollars of the 4 wealthiest people in a particular country are 33, 29, 16, 11. Assume that samples of size n equals 2 are randomly selected with replacement from this population of 4 values. After identifying the 16 equals 2 to the power of 4 different possible samples and finding the mean of each sample, construct a table representing the sampling distribution of the sample means.
Perfect. Again, I've chosen something very small because otherwise it becomes very involved. The concept is to understand that mu of x bar ultimately becomes the same as mu. That's the idea behind that. So to do this, we do it without replacement. The number of outcomes will be 2 to the power of 4 because we do it with replacement. So 33 can go with itself. Then 33 goes with 29. 33 goes with 16. 33 goes with 11, and 33 is done. The next number is 29. 29 can go with 33. 29 can go with itself. 29 goes with 16. 29 goes with 11, and so this is 4, this is 8, and there are 8 more. I didn't have room for that, but I hope if you pay attention to this, you can figure out the rest of it. So that's how it works. Each one has a probability of 1 out of 16. Each one of them has a probability of 1 out of 16. But I'm going to go with the column and show you this is how it's going to change. If you look at 33, there is only one way. So it's 1 out of 16. But if you look at 31, there are 2 ways. When we get 33 and 29, or when we get 29 and 30, they both give us the same answer, 31. So this is 1 out of 16. This is 1 out of 16. So the answer is 2/16. In other words, any number with itself, there's only 1 out of 16. But with any other number is 2 out of 16. For example, 29 with itself is 1/16, so on and so forth. So this is the probability distribution table. Compare the mean of the population to the mean of the sampling distribution of the sample means. This is called the sampling distribution of the sample means. So how do you find the mean of those 4 numbers? Add them up, divide by 4. Mu is summation of x over n, this number plus this number plus this number plus this number. Divide by 4 and we get 22.25. That's the average, of course, in billions of dollars. How do we find the average of the sampling distribution? I hope you realize mu was summation of x p of x. So mu of x bar with the same token would be summation of x bar p of x bar, which means multiply these 2 numbers, multiply these 2 numbers, all the way to the end and add them up. So 33 times 1/16 plus 31 times 2/16 plus, of course, everybody knows 2/16 is 1/8, but I just wanted to show you where the numbers come from, okay? And the last one is 11 times 1/16. When you do that, you get exactly the same answer. So mu and mu of x bar are identical, 22.25. What does it mean? Do the sample means target the value of the population mean? In general, do sample means make good estimate of population means why or why not? Yes, the sample means target the value of the population mean. That is, the mean of the sample means the expected value of the sample mean is equal to the population mean. In other words, mu of x bar equals mu. I want to make sure we understand what that means. So we want to know the average of these numbers, okay? If you look at those four and take the average, whereas looking at mu of x bar, if you take the average of all of those numbers, and the way you take the average, remember, you add them up, divide by size. So you have to add those numbers, and divide by 16. But when you get to 33, you have one of them. 31, you have to say 31, and you have two of them. 31 plus 31. 29, you have one of them. 24.5, you have two of them. And then you divide by 16. It's the same as multiplication of these two. And they are identical. Could somebody read the question, please? Go ahead, class. The population of current statistics students has ages with mean, mu, and standard deviation. Sigma samples of statistics students are normally selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does the central limit theorem, CLT, tells us? Tell us about the distribution of those mean ages. So CLT. Central limit theorem. Well, first let's discuss the central limit theorem. Anybody wants to read the CLT for us? Okay. The central limit theorem, a sampling distribution of sample means, is a distribution obtained by using the means computed from random samples of a specific size taken from a population. For samples of size n larger than or equal to 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. Here's the conclusion as a result. The distribution of sample x bar that we looked at an example in the previous page will, as the sample size increases, approach a normal distribution. The mean of the sample means, the mean of all of those sample means is the population mean, mu of x bar equals mu. The standard deviation of all sample means is sigma of x bar equals sigma over square root of n. Therefore, for this question now, we know n is 44, which makes it larger than 30. So a sampling distribution of the mean ages can be approximated by a normal distribution with mean mu of x bar equals mu, and a standard deviation of sigma of x bar, sigma over square root of n, or sigma over square root of 44 for this question. Where does the 44 come from? It's been given to us. Anybody want to read this one? Please, somebody read it for us.
A boat capsized and sank in a lake. Based on an assumption of a mean weight of 137 pounds, the boat was rated to carry 500 passengers. So the low limit was 137 multiplied by 50 equals 6,850 pounds. After the boat sank, the assumed mean weight for similar boats was changed from 137 pounds to 170 pounds. Assume that a similar boat is loaded with 50 passengers, and assume that the weights of people are normally distributed with a mean of 174.1 pounds and a standard deviation of 35.1 pounds. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds.
Perfect. So this is quality control, looking at what's happened and making a decision statistically. So what is given? We are dealing with the normal distribution, ND. N is 50 passengers. Mu is 174.1 pounds. Sigma, 35.1 pounds. And we want the probability of X bar larger than 137. Notice the 50 passengers have a mean weight greater than 137. Because N is 50, we go with mean probability of X bar larger than 137. So to go to the Z-score, we use the formula Z is X bar minus mu of X bar over sigma of X bar. So 137 minus 174.1 over 35.1 over the square root of 50, according to this formula. Again, remember, mu of X bar and mu are the same. Sigma of X bar is sigma over square root of n. You do the math, you end up with negative 7.474. And that's almost 1 or 100%, because when you go to negative, remember, if you cover 3 standard deviations on both sides, it covers almost everything, 99.7%. So you're somewhere here, negative 7.474, that covers everything. So the answer is 1 or 100%. The boat was later rated to carry only 15 passengers, from 50 to 15. And the load limit was changed to 2,550 pounds, which is 170 times 15. Find the probability that the boat is overloaded because the mean weight of the passengers is greater than 170. So that their total weight is greater than the maximum capacity of 2,550. That's really the concept. So again, it's a normal distribution with the same situation, but this time, the same as this one, this time N is changing to 15. So we repeat the same thing, but we are changing N. Same thing, we are changing N to 15. And of course, they want to go with number 170. Over here, we are changing this one, probability of X bar larger than 170. So we go to this formula and we calculate the Z, which is X bar, which is 170, minus mu of X bar, which is 174.1, over sigma, which is 35.1, over the square root of 15. You put it into a calculator, you come up with this answer. And again, you can graph this, use a table technology, and you end up with a 0.6745. So it's somewhere here now that you calculated. Do the new ratings appear to be safe when the boat is loaded with 15 passengers? The answer is no. Why not? Because there's a high probability, this is 67.45%, there's a high probability of overloading. The new rating do not appear to be safe when the boat is loaded with 15 passengers. At an airport, question number 11, at an airport, passengers arriving at the security checkpoint have waiting time that are uniformly distributed between 0 and 10 minutes. All of the different possible waiting times are equally likely. That's the concept of a uniformly distributed. Find the probability that the randomly selected passenger has a waiting time of at least 7 minutes. So let me give you the synopsis of the uniform distribution. Could somebody read this, please? Go ahead, class. Somebody read it, please. I know you can do it. Go ahead. Okay. No one feels like reading for us? Uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. Properties of uniform distribution. Density curve. The graph of any continuous probability distribution is called a density curve. And any density curve must satisfy the requirements that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there's a correspondence between the area and probability. Therefore, probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Area is height times the width. So what is given? The total area is 1, and we know the width is 10 minus 0, or 10. So the height must be 1 over 10, which is 0.1, because their product 10 times what number is 1? The total area is 1, right? 10 times 0.1, or 1 over 10. So this is the graph. Since this is between 0 and 10, the height must be 0.1. This may not be to scale, and that's not important. But the area must be 1. If this is 10, this must be 1 divided by 10, which is 0.1. We want the probability of waiting time of at least 7 minutes. That means probability of x larger than or equal to 7. That means from 7 all the way to the end, which is 10. So we want this area. So the height is fixed at 0.1, and this distance is 3. So the height times the width of the shaded region, 0.1 times 3 is 0.3. So the answer to the question is 0.3, or 30%. That's the probability. Somebody wants to read this? Anyone? No one?
Information regarding standardized tests used for college admittance. Scores on the SAT test are normally distributed with a mean of 984 and a standard deviation of 204. Scores on the ACT test are normally distributed with a mean of 20.7 and a standard deviation of 4.3. It is assumed that the two tests measure the same aptitude, but use different scales. If a student gets an SAT score that is in the 65 percentile, find the actual SAT score, full number.
Excellent. So first, let's see what is given. So when we look at the SAT score, we see that it's normally distributed. Mu is 984, sigma is 204. So we write it down. So it's extremely important you spend enough time to write the given, understand the question. So that's for SAT. For ACT, we write the same thing. It's normal distribution, but the mean mu is 20.7, sigma is 4.3. So that's understanding the question. So if a student gets SAT score, so we are dealing with this of 65 percentile. We want to find the actual SAT score. So that means 65 percentile. We're going to come up with the area. Okay, 65. The area is 65. This area is 0.65. So and so this is the z-score we are going to find using technology or the graph. So we have the area, we want to come up with the z-score. And from the z-score, we're going to go to x. So area to the left is 0.65. We are looking for the z-score anyhow you can. So after we find the z-score, then we go to the x. Remember, z is x minus mu over sigma. So z is x minus mu over sigma, or x is mu plus z sigma. So I hope everybody can see the process. So with that being the case, everything that we want to calculate this is here, we're going to use this one, except the z. So now we find the z from the table or technology. So mu is 984, sigma is 204 because we are dealing with SAT. That's why we're going to use the SAT stuff. From the technology, if we use the area of 0.65, mu is 0, sigma equals 1, it gives us the z-score of 0.38532 and so forth. So you want to go as many decimals as you can. So you plug in here mu, you plug in here sigma, and the z, we find it from here. And now since they want with whole number, after we find that we want whole numbers, 2 next to it is 6, so it goes to 1063, and we're done. So the process, graph will help us find the z, and in this formula, we can find x. Now the next one says, what would be the equivalent ACT? Now, this number, how would this number be represented if we are dealing with ACT? So I hope you see what the question is asking us. So an SAT score of 1063 corresponds to ACT score of what? That's the question. So again, we have to find the z, but the z was already found. So from the z of this previous step, we're going to go to x of ACT. So now we're going to use this with the same z we found in part A. So in this one, we are going to use ACT, mu, and sigma, and the z-score from part A. The z-score from part A is the same. And 22.36, we want to go with 1 decimal, so it becomes 22 point. We're going to change the 3 because of 6 to 2, 4. Be very careful when you do the rounding. You should know the round. If a student gets SAT score of 1494, remember we found this one. They already gave us this now instead of going through the process. So we have SAT of 1494. What is the ACT score? So basically now from here, you're going to go back to work backward to go to the Z from the SAT score. This is your X in essence. You're going to go to Z, and from the Z, you go to the X score of ACT. So I hope everybody understands the concept. So Z equals X minus mu over sigma. We have, for the blue one, mu and sigma, and the X score is 1494. So 1494 minus 984 over 204, the Z score. So this number, this SAT score has a Z value of 2.5. That's the idea. Now the same Z for ACT, you go with this formula, and then you get here, and X is mu plus Z sigma, but now you use it here. X is, I'm looking at this formula, mu, which is 20.7, plus Z, which we found it to be 2.5, times sigma of 4.3, 31.45. We want 1 decimal, so 31 point. We're going to change the 4 to 5 because next to it is 5. It means SAT score of 1494 corresponds to ACT score of 31.5. That's the meaning of it. Could somebody read this, please?
A Food Marketing Institute found that 35% of households spend about $150 a week on groceries. Assume the population proportion is 0.35 and a simple random sample of 300 households is selected from the population. What is the probability that the same proportion of households spending about $150 a week on groceries is less than 0.38?
Perfect. Well, let's see what's given. We have a couple of different ways of approaching it. Number one, 35% of the households spend about $150 a week on groceries. So this is a binomial distribution with P being 0.35. And we are looking at n of 300. So there are two different approaches, and I'm going to show you quickly. First, we want the probability of a p hat because it's going to be less than 0.38. What is the probability that is the sample proportion of households spending about $150 a week on groceries less than 0.38? So sample proportion versus population proportion. So what percentage, what proportion? So it's less than 0.38. Well, we can go to the z-score just the way it is by finding the following. First and foremost, notice that Q is 1 minus P as always, and it's 0.65. NP and NQ, I didn't show that, but if you multiply these two numbers, and if you multiply 300 by 0.65, both of them are larger than 10. Therefore, you can approximate it by normal distribution. Now, the formulas, I remind you, mu sub P hat is P and sigma of P hat squared of PQ over N. So these are the formulas. You can find them in your formulation. So mu of P hat is P. That means it's 0.35. Sigma of P hat is square root of 0.35. Square root of 0.35 times 0.65 divided by 300. And that's the number. Why do we need that? Because of the z-score. Now, if you want to go with the technology, I'm going to show you the z-score in a moment. If you want to go with the technology, the normal CDF minus 1 E99, that means a very small number, upper is 0.38. You can even use 0 here because you're talking about proportion class. Okay, it doesn't recognize that you're talking about proportion because it's normal CDF. Mu is 0.35. Mu is 0.35. Sigma is this number, 0.027538. And it gives you this answer. I want you to hold on to this answer for now. Because the second method is to calculate the z using x minus mu over sigma. And so p hat minus p over sigma of p hat. So p hat is 0.38 minus 0.35 over sigma of p hat. And that gives us this number, 1.0894. So this is the same as saying probability of z less than this number. And now you can use, instead of mu of 0.35, you can use mu of 0 instead of sigma of 0.027538, 1. Notice I'm just changing mu and sigma. And the upper value is this number. And look at the number. So look at those two numbers. And we put it here if we go with so many decimals. For example, if I want to go with the fourth decimal next to it is 1, so I keep it. So there are two different ways of approaching it. According to a survey, 10% of Americans are afraid to fly. Suppose 1,100 Americans are sampled. What is the probability percentage that 121 or more Americans in the survey are afraid to fly? So you're either afraid of flying or not. So right away, we have to understand it is a binomial distribution with P being 10% and N is 1,100. So anytime you claim binomial distribution, you have to write N and P. And I put them in the order that I received. What is the probability percentage that 121 or more Americans in the survey are afraid? There are a few different approaches, and I want to show you all of them. So X equals 121. There are three methods. When X is 121, P hat, if you remember, is lower X over lower N. So it's 121 over 1,100, and it becomes 0.11. So we want probability of P hat larger than or equal to 0.11. What is the probability percentage that 121 or more. So in other words, we change this to a p hat. P hat is larger than or equal to 0.11, and we use the information from the previous page, finish the job. That's one way. Let's do that. So mu of p hat is p, but sigma of p hat is square root of pq over n. And so p is 10%, q is 90%. You plug it in here, and n is 1100, and this one is the same as p. So that's 0.1. This is 0.1 times 0.9 over 1100, take a root. And so that is the sigma of p hat. Now, we just use the technology. So the lower, on purpose, see, the lower we can use 0.11. The upper, on purpose, I used 1, just because we are looking at proportion, and it really can't go over 1. But this one doesn't recognize that. You can use any number larger than 1. Normally we, since we go to infinity, we use 1,000 or 10,000. But the reason 1 works because you're dealing with proportion. So mu is 0.1, mu is 0.1, and sigma is this number. And you get this answer. And again, I want you to know, upper I'm using 1 because it's a proportion. Remember, proportion is between 0 and 1. So 1 will work. But if you use the 1,000, the reason it works because it's normal CDF, it doesn't recognize you're dealing with proportion. Here's the first method. Let's look at the second method. Z equals x minus mu over sigma. Z is p hat minus p over sigma of p hat. And so we calculate the Z score. So from p hat, we're going to go to the Z score. Okay, so this was the first method, probability of p hat larger than 0.11. The second method says probability of Z larger than or equal to then this Z score, and you can use the Z score. Also, I'm going to remind you of that 0.5 continually correction factor. If you recall, if we go with this one, just the weights given. Probability of x larger than or equal to 121. Remember, we are going to go to normal distribution, which means we are going to add 0.5 or subtract 0.5. If I, and that means from 121, please understand this means P of 121 all the way to the end. I'm interested in the first one. So if you change this to 1, $120.5, or change it to 121.5, what happens? Here's what I want you to notice. If I change it to 121.5, the first number larger than this, which is discrete or a whole number, is 122. I'm going to miss 121. But this one, the first number is 121, so I'm going to go with that one. Okay. And now, again, I can go with x minus mu over sigma to change it to a Z score. And the Z score must be the same as this one, and it is. Or it's almost the same. The lower is this number, and the upper we're using 1,000. Mu is 0, sigma equals 1. And that gives us the answer here. And take a look. The two answers here. And if we go with a bunch of decimals, for example, if we stop at 4, next to it is 6, it goes up to 5. As you can see, they are almost identical. So there are different approaches. You can use the approach of proportion, or just the number that is given, and the normal distribution. You have to add or subtract the 0.5 continually correction factor accordingly. Here's the last question, last part of this question. We're looking at the same question. What is the probability percentage that 165 or more Americans in the survey are afraid to fly? We're going to look at that, and we don't have to look at it both ways. So P hat In this case is 165 over 1100 or 0.15. So we want the probability of p hat larger than 0.15. If you go with the z-score, using the formula of p hat minus p over sigma of p hat. P hat minus p over sigma of p hat, using the formula from the previous page. Here's the z-score. And normally, if it's beyond 3, the answer is really 0. So from the table, it's almost 0. I want you to know that. If you go with the normal CDF, using this one, take a look, using this one, you put 0.15, and the upper you can put 1 because it's a proportion, or you can put 1,000, and it gives you the answer. Okay. If you go with the z-score of 5.52773, upper is 1,000 and paste it. And both of them will give you the same answer. Take a look at the number, 1.626070611. E minus 8 means this number, I want to make sure everybody understands what number is given to us, means this number times 10 to the power of minus 8. That's the meaning of this, which is an extremely small number. It's almost 0. So let me clean up. So because of this, that means almost 0. So 0.00%. What is the probability percentage that 8% or less of the Americans surveyed answered they were afraid to fly, and rounded to 2 decimal places? So we want to pay attention to that. So we are interested in this probability of p hat less than or equal to 0.08, and we can stick with that and use the technology because we have shown work before. So lower is 0, upper is 0.08, and again the reason we can use 0 because we're talking about the proportion. Mu is 0.1, sigma is sigma of p hat, or you can even put the lower, instead of 0 you can put minus 10,000 because it doesn't recognize that you're dealing with the proportion. It's a normal CDF. And just again, the only reason I want you to pay attention to this one and this one, and why I have 2 different values. It's normal CDF. Normally we go with this one, but the reason 0 works because you know it's proportion. Okay, proportion is between 0 and 1 only, including the endpoints. Both of them will result in this answer, 0.0135. And we want to write it as a decimal. So it's this moves 2 decimals and becomes 1.35%. 1.35%. That's it.